What you are seeing is a smart light being controlled in real time. The smart light is indicating the vibration information from the system by a virtual PLC running on the reComputer edge device. No proprietary PLC hardware, no expensive licenses, just OpenPLC, an IO-Link master, and MODBUS TCP/IP communication. And in this video, I'm going to show you exactly how I built this. My name is Rajveer, founder of Code and Compile, and in this video, we're going to talk about real-time vibration monitoring using MODBUS TCP. So if you've seen my last video, I showed you how to install OpenPLC runtime on reComputer and how you can write your first program, and also how you can connect that to Simomatic via OPC UA. If you haven't seen that yet, please go and watch that video. I'll put the link in the description. Go watch that because this video is built on top of that foundation. All right, you need to see that first before continuing here. So here's what we are doing today. We are going to read real-time vibration in virtual PLC via MODBUS TCP. We have our virtual PLC as OpenPLC runtime, which is running on my reComputer. It's the same device like I was using in the last video. But now, instead of just doing the simulation or just running a dummy logic, I'm connecting that to a real hardware. So I have Balluff IO-Link master, which is connected to several sensors and actuator I'm going to show you shortly. And I'm communicating my virtual PLC with this IO-Link master via MODBUS TCP to read the data. All right. So let's understand the system architect, okay, how this has been connected. There you go. So now you can see that in the center, I have my reComputer running OpenPLC runtime. So virtual PLC instance is already running here. And this is what I've explained in the last video. So if you notice here, you have two Ethernet ports on this edge device. One is Ethernet 0. This is connected to the web. So that's how I deploy my program. So I will create the program in my web browser and I will deploy it directly to my edge device because edge device has a connection to the internet via this port, right? And the other port, which is isolated, this is connected directly to my IO-Link master. All right, so this port is like industrial Ethernet port. And this is communicating via MODBUS TCP/IP. I will show you shortly how you can do that. And I have not shown you here, but I'm also connected to this network with my laptop so that I can show you how you can access the web server. So it's not mentioned here, but my computer is with another extra port is also connected to this network. So these are the IP addresses. This is the IP address of my edge device for my Ethernet 0. This is for Ethernet 1. And you can see that the IP address of virtual PLC has its own IP address, and this is running in the edge device. All right. And on the right side, you will see, if I just maybe remove myself for a second, you can see my IO-Link master is powered up by 24 volts. And this is connected to my smart light, which is connected to port 1. And port 2 is connected to photoelectric sensor, and port 3 is connected to a condition monitoring sensor. This is going to give me a vibration data and temperature data. And that's the IP address of my IO-Link master. So currently, if you see on my trainer, I already have all these devices connected. And you can see that the LED status, the IO-Link master is working, and my smart light has some green indication. This is also fine, right? Now, before I jump into the programming, first I wanted to show you the data that is coming to my IO-Link master. So in this case, let me just open up my web browser. So right now, I just entered the IP address of my IO-Link master, like I told you that I have access to this one, and this opens up the web server. This makes it easy to parameterize my devices. So I've already installed the IODD file, so it's up and running. I will not go that detail into that. So let's just log into this device. And I just want to show you the data coming in. So now my vibration sensor, you can see that it's connected to port number 3. Let's open this one. And here you can see I have some values. Here you can see that this is the vibration in X, Y, Z, and that's the temperature. So now if I add some vibration, so I don't have this sensor is not connected to the motor, but I just tap on my trainer, and you can see that the vibration changes, right? In real time. And you can see that there's an indication which also changes. That is the logic I'm going to talk about. So this indication shows what kind of vibration you're having in your system. So this is data is coming in real time. Just wanted to show you. And similarly, my other devices are also connected. This is my port 1 where I'm connecting my smart light. And here we can see there are some parameterization. You can read the parameters, you can write the parameters. This is running right on segment mode. I have reduced the brightness because I have to capture that in my camera. And there are 5 segments here. So I will talk more about that, what I'm doing in the smart light later on. So just to show you that my devices are up and running. So data is coming to my IO-Link master. Now, how to get this data to my PLC? Now remember, I'm using MODBUS TCP IP. And this is a very fast communication, but this comes with a challenge. The challenge is the data that I'm reading in my IO-Link master is from a vibration sensor, which is coming in float. So you can see the value I've shown you before. But when I'm sending the value via Modbus, you can't send via float. You have to send in integer. So I am sending the value in integer, but then I convert it back to float in my PLC. So I will show you the program, how you can do that. You can also take a copy of my logic. You can implement the same code everywhere where you want to use. All right, so now let's understand first, before I jump into the PLC programming, what are the addresses I have to read. So if you're using IO-Link master from Balluff, this video will be helpful because I was playing around with this IO-Link master and I find out some addresses that will be useful for you as well. So let's jump to this next slide, Modbus registers for smart light. So for smart light, I have Modbus registers starting from 1117, all right? So here, this register is going to enable this device. So this is a device activation bit, okay? If I send it to here 0, it will disable the device. If I send 1, it will enable the device. This, I need that. And then you have 1118, which is linked to QW1. And this mapping, I will do that in the PLC. I just mentioned that here for my reference. This is going to define the mode. So now smart light, because it's smart light, it has various modes. There's a segment mode, there is an analog mode, there is a smart mode, ultimate mode. You can read that in the manual of this device to learn about various modes. The mode that I'm using is segment mode, in which I did some reduction of the brightness. So I have a unique number that I'm going to send to this register to activate my mode. And then I have 1120 to 1124, which defines my segment 1 to segment 5, which means what is the color of the segment or what is the animation type of the segment. This will be defined by these registers. Pretty good. So now the next slide, I have a photoelectric sensor. Let me just remove it. So this photoelectric sensor, I'm just reading the object detection. So I have 2 addresses, 1200, which tells me the status. And notice that it says IW 9 and 10 because this is an input value, input registers. So 1201 is the main register that I need for object detection. So this is what I need for my photoelectric. And the next one is condition monitoring sensor. This is the main sensor which I'm going to use. So in this sensor, I'm getting vibration data. So I'm getting VRMS in XYZ direction. And this is coming to the register. You can see that 1301, 1302, there are 2 registers. So what is IO-Link master is doing is it is splitting the float value into 2 registers, integers values. Okay, so float is split into 2 integer values. This is what I'm going to decode in the PLC. So my VRMS has 2 registers, high word and low word, so 2 word registers. And IW1 has a high word and IW2 has a low word. And similarly, VRMS also has 2 registers, IW3 and 4, and VRMS also has 2 registers, IW5 and IW6. And then you have temperature, which also has 2 registers, IW7 and IW8. So I have 8 registers that I'm going to use. And I have written a piece of code which will make it super easy to convert this register integer values to a float. All right. Now come to the main part. And this is where something a lot of people also confuse. So now here's something that, confuses me when I was trying to work on that. The vibration data from Balluff sensor arrives and split across 2 Modbus registers, as you can see on my screen. Each register is 16-bit. So together they form a 32-bit IEEE 754 float value, all right? But it's not a simple join. There is a byte swap involved. So you have to swap the byte. So the sensor signal data in big endian format, you can see that the format is ABCD here. We have to swipe the byte. So to read it correctly as a float in OpenPLC, we need to swap them. We have to make it to BADC. Okay, you can see that I've mentioned that here, in which AB is swap and CD is swap. So when you swap it, then you get the proper value. And if you don't do that, you will get some incorrect value. All right. So If you see here, I have mentioned verification. Let me just remove my saw because I might be hiding the text. So you can see that register 1 XVRMS high word is 62 here. All right, this is 62. And register 2 XVRMS low word is -9446. So if you convert that to hexadecimal, this is the value. So this word also has low byte and high byte. Okay. Similarly, this register also has low byte and high byte. So because we are doing byte swap, we first swap this one. So 003E becomes 3E00, and DB1A becomes 1A DB. All right. So this is how you do the swapping. Don't be confused with the colors. I think this should be blue and this should be green. There is some mistake. And then if you convert that back to float, it will give you this value, 0.1251. This is my vibration in x-axis. All right. So this is what is very important, and this is what we're going to execute in the PLC now. So now let's jump to the PLC program and see how we can realize that. But this theory was a bit important to explain before I proceed with the programming. So let's create a new project. I will call it Virtual PLC 3. Put it into the code and compile folder. Next, select the language. I will go for structured text. Next, and let's keep it private. So I have my project listed here. Let's open that. It's a blank project. So I have already created this project. So I'm just going to copy paste my code because otherwise this video will be in about 2 hours long. So I will just copy paste my code here, and then I will show you how this code is working. But the main part here is because now this virtual PLC has to communicate with the remote IOs. I have to add a device. So I'll click on this plus, and first I will add a remote device. Let's call it Balluff. And the protocol that I'm going to use is MODBUS. Let's create a device. So TCP IP, and now I need the IP address of my IO-Link master. I know that by heart. I will just put it here. And port address for MODBUS for most of the devices 502 as default. Timeout, I will keep 1 second. Now I need to define the groups. So in this case, I'll click on the plus icon. And now first IO group name. So I will go with the first group, which means I will go with the first port. So the first port was connected, smart light. Okay. And smart light, because it's an output device, I have to have a function code of write multiple register because I'm writing to this device. It's an output device. So here I have a cycle time by default. I will not change that. Offset. Now for that, now I will go back to my presentation. So I will check my offset was 1117. And how many registers I'm reading? From QW0 to QW7. So 8 registers starting from 1117. Let's open that again. So this is the starting register. 8 registers the length. Error handling, keep last value. That's fine. So now you can see that I have mapped my Modbus register to PLC registers. So these are the registers I'm going to use in my main code. Super easy. And now if you want, you can also write the comments here. So, but this, I will not do that. Otherwise, this will take a lot of time. I will keep it as it is, but feel free to write a comment if you like. And now I will add another one, another group. So another group will be my port 2, which was my photoelectric sensor. So I'll just write here sensor. Here I'm reading the value. So let's go back to the presentation. So this is my port 2. Starting register is 1200. I'm reading 2 register, but the only register I'm going to use in my PLC program is object detection. So 1201. So I can check just 2 register. 12, and I'm reading 2 values. So I need to read this one. So I can just write here maybe detection. And now comes a third group. Third group is my vibration sensor. Here I'm reading the holding register because I'm not writing the value. One more time. Let's go to the final port. Starting from 1300, I'm reading 9 registers. The first one is the status, and then we have VRM's value. So 1300, and the length is 9. Great. And now you can see that this has created my mapping. Super easy. Mapping is done. Now we can jump to the PLC program. In this case, I have my main logic, and the conversion that I'm doing here is, now this is the important part, and this is the beauty of OpenPLC, that I'm going to use C++ program here inside my PLC. It is possible. You can write function block in different languages. You can use ladder logic, FBD, structure test, C++, or even Python. So if I click on plus, look at here the possibility of function block, ladder diagram, structure text, instruction lists, FBD, Python, and C++. So I'm going to use C++ because I have ready-to-use code, which I will just copy from my already created code, and I will put it here, and then I will explain you what is happening in the code. So let me just create a code, and I will just see the exact name that I was giving here. This will be WTOR. This is word to real, all right? Let's create that. And now you can see there's a default text here. Now I will just put my variables here in the text format, paste here. So I have two inputs in this function block, high word and low word. Like I was telling you, you send high word and low word and you get the real value. We send two registers and we get the real output. That's what this input and outputs are doing here. And now the code, I will just copy this here. That's the code. Now I will not go too much detail into that, but the main part is over here. So we have a high word and we have a low word. So the high word, we are extracting the low byte from this high word by doing the AND operation with this hexadecimal FF. With this, when you do the AND operation, you get the low byte out of it, okay? And with this shifting the value, you get the high byte of register 1. So from the high word, you get the low byte and the high byte. Similarly, from the low word, you get the low byte and the high byte. So we are extracting 4 bytes from 2 words because one word consists of 2 bytes, low and high. So high word has low byte and high byte, and low word has low byte and high byte. So we have 4 bytes. So if you see here, this automatically, the idea of doing this is to extract the sequence BADC because we are getting the sequence ABCD. So we are getting the sequence like this. First, we are getting B1 and then B0, then B3 and B2. But using this code, we change the sequence. So now the first element has B, the second element has A, third element has D, and fourth element has C. That's how we are extracting it. And then we just group it all together, and then we convert that to a real output. So that's how our conversion is going on. You can take this code if you like. I will put it in my wiki, and you can use that. I could practice that as well. And this will for sure work for you. This is for big endian byte swap example, all right? If you want to learn more about swapping, different types of swapping, I have mentioned a wiki article, which I will also put in the description of the video. You can go ahead and check that one. So this is just the conversion function block. Now we'll create another function block. This was for debugging. So we'll create a function block and let's call it PLC, or let me just see the name I was using in the last program, print logs. So there you go, program, print log, and I will also create C++. So in this case, I will just copy that, paste here, copy, paste. Maybe let's rename that to print logs. So this function is just going to display some values in my log. So I have a console log where I can display some values. I can remotely monitor the values, what is happening in my edge device remotely. Right now, the edge device is lying on my table, but this could be anywhere because the edge device is connected to the internet. And if you want to do some debug operation, you can print the values at your console log, and this is the function which will help me to do that. So now coming to the main logic. Now in the main logic, we have to do some variable declaration, which I've already done, and I will just explain you what is happening there. Copy, and I will just paste here. So notice that I have took several variables. So this is my word xvrms high word, xvrms low word, yvrms high word, low word, zvrms high word. So I have high word, low word of every axis for vrms value. And I just need to check if my mapping here is correct. So let's just verify that. This is showing IW1, which I think it's not correct because the sequence was not the same when I was doing the configuration there. So if you see vibration sensor values are starting from IW3. The first one was just the status. Let's just verify one more time. The first one was the status, and IW1 has my VRMS high word and low word. So IW1 to IW8 I have to do for Modbus. So IW1 to IW8, let's see that what is here. Here you have IW2 because I was using a sensor before here. So that's why it's taking this one. So I have to just change, or what I can also do is, because in the sensor I'm just using one value. Let's try one more thing. I will just take here as length 1, and I save it. This is my IW0, and let's define that again, then I will be fine. So let me just delete that. This is okay. Vibration sensor. This will be just more shortcut. So the offset was 1300. Length was, oh, we can take 1301 because in this case I don't need a status, so I can start with 1301, and the length I will take 8 registers. So now I have IW1. So if I go back here, this is fine, starting with IW1. So my mapping, I don't need to rename that here. So this is more shortcut for me. So mapping is done here. This is for temperature, and for the sensor, I have to change. This was IW0 for the sensor. Smart light is fine from QW0 to QW7. Let's just verify that. Sensor was IW0, smart light starting from QW0 to QW7. So my address mapping is fine. And then I have some variables here. So I'll show you what I'm doing here. Let's just copy the main code, paste here. So if you see the main code, I have some initialized value. So I activate my smart light, so I'll send 1 to that. And then I have a mode. So this number actually, when I was playing around in the web browser, I had a Modbus pole which was open next to the system. And in this Modbus pole, I can see the value. So you can see that the smart light is activated, and this is actually signed value. If I put unsigned value, 34049 reflects that my smart light has a brightness reduction of 80%, and it is working in the segment mode. All right. And these are the values. You can see right now the smart light is green, and I have 512. So I get this number here. This is not connected. I can also connect that. So I took this number from here. So when I change the light color, I get a different number, and I get this number, integer value, and then I use it later on based on what color I want. Okay. So mode has been defined, and threshold value is basically I define a threshold for vibration. If the vibration is less than my lowest threshold, which is 2.5, it means system is okay. If vibration is between 2.5 and 7.1, it means it's a warning. Please take care. If the vibration is above 7.1, it is going to be a critical warning. So it's going to blink red. So now to get the temperature, what I'm doing, I'm just calling this function, WTOR_convert. This has been defined here. So I will initialize my function block here. And I sent my high word as my temperature high word, which was defined over here. Temperature high word at IW7, and I send the low word. So I send 2 registers, like I was telling you before. And this function, WTOR, will give me a real value, which I'll get an R temperature, which is defined over here. So I get a real value. Similarly, I send the high word and low word for X VRMS, and I get the real value in RVRMS. Okay. Similarly for Y and Z. So I'm just getting the real value back from my function block. Now I have just a small code just for the demonstration of this video to find out the maximum vibration. So I will read if X VRMS is more than maximum, or Y or Z. So out of these 3 RMS value, I just look at the maximum value of vibration, and then I compare that with my threshold. Okay, I don't compare each vibration, although you can do that for more detailed analysis, but I'm just taking the maximum vibration and checking that with my threshold, which is over here. So if my vibration is less than threshold, or if vibration is between the thresholds, or if it's greater than thresholds, then I have defined a vibration state 0, 1, and 2. Very simple PLC logic. And now if the sensor is true, right now you can see that on my screen, if the sensor is true, it's green light, okay? And there is no vibration. That's why this else statement is going on, this one. So it's showing green. But if sensor is false, if I take away this device or just make the sensor false by bringing it closer, this code is running. 2304 is going to my smart light. That's why it's white, which means there is no product. This is just to include the sensor in this video. Otherwise, you can just ignore that sensor. But otherwise, now if I make some vibration, so let's just download the code. So for that, we need to first go to Orchestrator. Right now, the code is already there. That's why it's running. But let's show you live how to download that. So once you write the code, save the project, and go to the orchestrator. And this I have showed you in the last video, that you need to install virtual PLC instance, and then you will find this device here. It's up and running. I will just connect that. So you will get an ID and password the first time you will install virtual PLC. So this is connected. You can see the scan count, scan time. I will just now download it. So I downloaded a completely new project. It will override the last project. So everything is working fine. And if you go to the PLC log, you can see some conversion value. Like I was showing you, I'm printing the values. So these are the vibration values coming here. So if I increase the vibration now, you can see that the vibration values will increase. So this is now 3, but this is my vibration in Z-axis. And now you can also see the color is being changed. So the color is being changed because it is defined by this code. If there is less vibration or low vibration, there is no change in the color. So now you can see vibration here. And if I include some vibration, so this vibration is not too much. This is between 2 and 7. So this is 3.4. You can see that it's orange rotating light. And if I increase the vibration, if I do manually, you can see that it's blinking red. So the vibration value is 9.4, which is more than 7.1. You can see that the vibration is too much, and it is indicated on the smart light. So you can see that if your code is ready, fraction of minutes, you can deploy that into your edge device using OpenPLC runtime and do some amazing things. All right, so this was how you can connect to your remote devices using OpenPLC via MODBUS TCP IP. I hope you find this video useful, and if you want this piece of code that I have written here, I can put this into my Wikipedia and you can take out from there. Now let's zoom out for a second and talk about why this actually matters. So what we just built is the foundation of predictive maintenance. Vibration monitoring is one of the most common techniques used in the industry, because this is going to tell us earlier failures. This is going to give us a sign of failure of any machine, rotatory machine, or pumps, or conveyor drives, or compressors, anything where there's some motion going on. Because if you ignore that, there will be a failure and there will be a breakdown. All right. So traditionally, if you build such system, you need a dedicated PLC, you need a SCADA system, you need a proprietary software licenses, and that comes with the budget, right? And most importantly, you have to be at the location to do the commissioning and installation. But nowadays, with the most latest technology, you are able to remotely program your PLC with a solution like OpenPLC running on the edge device, like a reComputer. You don't need a real PLC. You can just work on the edge device. And other hardware is the same. You have IO-Link Master from Balluff, which is handling the sensor layer or the actuator layer. And you can build this for a fraction of the cost using open standards like MODBUS TCP, OPC UA, IO-Link, and using IEC 61131 programming standard, right? Everything is open, all standard. And this is just the beginning. In the next video, I'm going to show you how you can take it to the next level. So maybe I will write some posts or show you some small videos where you can make a dashboard with your data, with the vibration data, and you can show how you can generate alarms automatically based on the vibration data. You can generate some alerts as well. So for that, I'm going to use a dashboard from ThingsBoard, which I've done. I've also made one post before on my LinkedIn. So I'm making this series of video to show you from step by step how you can extend your architecture. All right. So if you want to see that, make sure you're subscribed and you're following me on LinkedIn. And thank you for your attention and watching this video. I have linked all the documentation in the description of the video for the IO-Link Master, for OpenPLC, and for this conversion. All the code, you can find this in my Wikipedia. So if you're doing this, I would love to know what sensor you're using, which edge devices you're using. Feel free to connect and write a comment or write me on LinkedIn. So thank you for watching, and drop me a comment if you find this useful. I'll be motivated for the next content as well. I read every comment myself. So thank you for watching, and I hope to see you in the next video. Until then, have fun. Bye-bye.